So today I am going to explain about what is the displacement thickness. In this video I am going to explain about the displacement thickness, and I am Sushan Lal Babu, Assistant Professor, Aerospace Division, Karunya Institute of Technology and Science. So before going to the displacement thickness, we should just an introduction to the boundary layer thickness. And you can see that boundary layer thickness, so this is a flat plate. You assume it as a flat plate. This is a flat plate, okay, where no slip condition exists and over which the boundary layer formations, this is the layer over which, so this is transition, okay. Boundary, this is the boundary layer region. This much, this particular region is called the boundary layer region, okay. So this flat plate is extended like this, so it is the flat plate, okay. So this is the flat plate, okay. It's flat plate, okay. This is a leading edge, okay. This is a leading edge, and boundary layer is formed, and we use shell to 0.99% of thickness. So next we are going to, this is what is called boundary layer thickness, delta, okay, delta. Next is displacement thickness. So displacement thickness, we can explain it as, consider a cross section, okay. This cross section I am saying, okay, the one cut section I am taking and I am viewing from this direction. If I am viewing, viewing from this direction, I can see this region. I can see this region like this, okay. I'm viewing from this side. I'm viewing from this side, and I am seeing a portion like this, and okay. So this, you can see this length delta. This is the length delta. This is the length delta, and this width of the plate is nothing but b, okay. Width is b, and I am considering a small strip, okay. This is a small strip of thickness dy, okay. This much length is here, from here to here it is, here to here it is y. At y distance, a small strip of dy I am considering, and through that, that strip, flow is coming out at velocity u, okay. This is nothing but u is nothing but this strip, because these regions are, see this region or that brown color region are at this much region, it is free stream only, but this is boundary layer region. So boundary layer region, u will be small u always less than capital U. That is what they are saying, okay. Anyway, this through the strip, a u velocity, at u velocity, flow is coming out. Next we have to find how to calculate mass flow rate coming out through the strip. How we can find mass flow rate? Mass flow rate is nothing but rho into a into v. So what is density? Density will be given, fluid has a constant density, dot area we have to find. What is the area of this? So what is the area of this particular region is nothing but rho into area, that is bit into p into dy. So into velocity, if you multiply small u, density into d into u is the m dot, okay. That is what I explained in the next step, okay. That is dmu. You will get it as dmu, mass flow rate, differential mass flow. It means very, that through that thickness of, sorry, the layer of thickness, a strip of thickness dy, the dmu is the flow rate happening, and nothing but rho into area. This is area into sorry, this is area into small u, dmu, okay. The fluid moves with u. If there is no boundary layer formation, it has to move with capital U, and if it is moving with capital U, then what will be the flow rate? D rho into E into D by capital U. So what is the loss of flow rate happened because of this boundary layer formation? dm is equal to dmu minus capital U minus small u, that is, it will becomes rho into B dy into U minus U. So what do you have to do? So we have calculated dm. So if the change in flow rate across this total length, across this from here to here, you have to integrate, and we have to integrate, see, you get to integrate from 0 to delta, and the rho b d by u minus u. So or m is equal to rho b into, rho b is a constant, so we can take it out, and 0 to delta u minus u dy, okay. So m becomes rho b integral 0 to delta u minus u dy. And next what we are going to calculate is that, so to accommodate for that loss in mass flow rate, the boundary layer has to, or the fluid has to shift a distance of delta star. Okay, we have identified, actually we have identified what actually we have identified the um, we have identified the uh, change in mass flow rate. Okay, change in mass flow rate. To accommodate that change in mass flow rate, the conservation of law has to be valid. Okay, mass conservation has to be valid. So if we some velocity reduction is happening, then definitely it has to, the boundary layer has to change to accommodate that particular velocity change or mass flow rate. The velocity reduction is happened, velocity reduction has happened within the boundary layer. So velocity reduces means what? Mass flow rate will also will get reduced. But conservation law states that m dot or m has to be conserved. If some reduction, we can't say that mass reduced. Inlet and outlet mass has to be constant. So to keep the mass flow rate constant, what we have to do, it has to shift the velocity, sorry, boundary layer or fluid has to shift, and it has to, that shifting distance is nothing but displacement thickness, how much it shifted to accommodate for that reduction, change in mass flow rate. Okay, that is what. So what is the mass flow happening through this region? So we can calculate. So u is the, capital U is the free stream velocity happening there. So what is density into area into velocity? So density, area is nothing b into delta star. So density into b into delta star into u is the, this value is the mass flow rate happening through this region. Okay, how much reduced within the boundary layer is accommodated here. Okay, so that we are equating, this is what change happened within the boundary layer because of the formation of boundary layer. This is the thing happened because of BL formation. Okay, so this is BL formation, and that is accommodated or compensated by a small shift in the fluid layers with that delta star. Okay, so if we equate delta star, we will get 1 by u into u integral 0 to delta 1 minus u by u dy. Okay, that delta star is nothing but u cancels, and 0 to delta 1 minus u by u dy. So displacement thickness of the boundary layer flow is the distance by which the flow has to be displaced in perpendicular direction of the surface to compensate the loss of the flow due to reduction in the velocity caused by shear force exerted by the surface over the flow. So because shear force is the reason for the viscous effect or viscosity or drag, and because of the drag velocity reduces. So some mass flow reduction is happened. To compensate for that reduction, fluid has to shift in the normal to the surface, and that shifting distance is called as boundary layer, or sorry, displacement thickness. And that displacement thickness can be calculated from 0 to delta 1 minus u by u integral 0 to delta into 1 minus u by u into dy. Okay, thank you.